Hello friends. So today we are going to discuss three questions and these three questions are from the year 1985 and we have 1983 and we have from 2011. So the first question, which was asked in the year 1995, and the question is: space is divided by line AD into two regions. Region 1 is field free and region 2 has a uniform magnetic field B directed into the plane of the paper. ACD is a semicircular conducting loop of radius r with center at O. The plane of the loop being the plane of the paper. The loop is now made to rotate with a constant angular velocity omega about an axis passing through O and perpendicular to the plane of the paper. The effective resistance of the loop is R. So based on this description, we have three questions. First one is obtain an expression for the magnitude of induced current in the loop. Second is show the direction of the current when the loop is entering into region 2. And the third is plot a graph between induced current and time of rotation for two periods of rotations. So we are given a figure. There are two regions, region 1 and region 2. Region 1 don't have the magnetic field, so here B is equal to 0, whereas region 2 has a magnetic field B and that is into the plane of paper as a perpendicular. And we have a semicircular ACD and it rotates with angular velocity of omega.
There's nothing to stop here. Check if the device is on your home Wi-Fi network.
Oh, sorry about that. And we have to region B, and we have semicircular disk which is ACD and it is rotating in region 1 as well as region 2 continuously. So first of all, we are given that we have a loop ACD . We have loop ACD and which is semicircle having radius small r. Small r. And there are two regions. Region 1, which is no magnetic field, and we have region 2, uniform magnetic field directed into plane of the paper. Uniform magnetic field directed magnetic field B directed into the plane of the paper. Okay, so it is also mentioned that the loop rotates. So we are given that loop ACD rotates at a constant angular velocity omega about the axis which passes through O and also perpendicular to the plane of paper about the center O. So it means as the loop rotates, different segment of it will move in and out of the magnetic field. So because of this loop rotation, we can say different segments of it will move in and out of the magnetic field leading to change in flux. Leading to change in flux, and because of this, which induces EMF and current, which induces EMF and current. So let us first of all find out the magnetic flux through the loop. Magnetic flux through the loop. So in this case, we assume let the radius vector is making the angle of theta with the line AD. So basically means if this is our line AD and loop is something like this, and this radius vector is making an angle of theta with the vertical line, that is AD. Okay. So we say at any instant let the angle made by radius vector with line AD is theta, which can be written as omega multiplied by time t. Now we can also say rather that the area of the loop in the region 2 varies with time, okay, because it is going to rotate in this direction with omega, and this is our region 2, and here we have region 1, and region 2 consists of magnetic field. Therefore, the area of loop in region 2 varies with time. And the area of loop in region 2 varies with time. So we can write that this area will be dependent upon angle theta. So area with respect to angle theta will be equal to half r square theta. And here theta is angle in radians, or we can also say that this because this will be resulting in the formation of sector. So we can see area of sector will be equal to half r square multiplied by theta. Therefore, the magnetic flux through the loop let us call that phi b through the loop we can say our phi b is equal to b, area which is theta is equal to b multiplied by half r square theta. So this is our magnetic flux, and we already know that our theta is equal to omega t. So we substitute, we get a magnetic flux B will be equal to half br square multiplied by omega t. Now we know the flux, we can find out induced EMF. Induced EMF, this will be equal to minus derivative of flux, rate of change of flux basically. So we substitute value of phi b, we get induced EMF is equal to minus dy by dt of half br square and multiplied by omega t. So we can derivate it, and this will be giving us minus half br square multiplied by omega. But in this case we are only mainly interested in magnitude, therefore we can write that our flux will be equal to not flux but induced EMF br square multiplied by omega. Now we can find out the induced current. Induced current, if it is given as I, will be equal to induced EMF divided by resistance R. Induced EMF we already know. We can write this as half br square omega divided by resistance R. So this is the value of the induced EMF. So I think in the first part this was only asked thing. Yeah. So in part B we are only asked the induced current, the loop. So the current induced in the loop is equal to half br square omega divided by R. Now we come to the part B. In part B, so as the loop enters region 2, magnetic field passing through the loop is going to increase, because this is our initial position of the loop rotating in this direction with omega, and we have a magnetic field here. So this is our region 1 and we have region 2. So as the loop will start to rotate, the area, or we can say the magnetic field passing through the loop, is going to increase continuously. We can say that when loop enters the region 2, magnetic field passing through the loop is increasing. Therefore, according to Lenz's law, the induced current will be produced such that it is going to oppose this increase. So obviously it will be in the current will be in the anti-clockwise direction. So we can say from Lenz's law, the induced current will produce magnetic field such that the current is in anti-clockwise direction, such that induced current is in anti-clockwise direction. This was a part B. And in part C, we are supposed to find out that plot the graph induced when the time rotation for 2 periods of rotations. Okay. In this case, you can say that is a part C. We start with the half rotation. So you can say for half rotation, time which is equal to total time period divided by 2, and this comes as pi by omega. The current in the loop will be of constant magnitude and anti-clockwise. The current in the loop will be constant in magnitude, which we found out that our I will be equal to b omega r square upon 2r and anti-clockwise. And anti-clockwise. And in the next half rotation, the loop comes out of region 2 and moves into region 1. So current will be in the clockwise now. You can say in next half rotation, when the loop comes out of region 2, the current will be clockwise now, but the magnitude will be constant. So if you take anti-clockwise as positive, So if we take anti-clockwise as positive, therefore we can draw the graph as this is current over I, maximum peak value is our b omega square upon 2r. So here we have b omega r square upon 2r, and here negative will be of same magnitude, minus omega r square upon 2r, and this will be our kind of a square wave. Something like this. So here we are going to have pi by omega, and then by 2 pi by omega. Here we are going to have pi by omega. This is our 2 pi by omega and 3 pi by omega, and this will be our 4 pi by omega. So this is for 2 rotations. Current time graph for 2 rotations. So this completes the first question. The second question, which was asked in the year 1983, and here it is given that a square metal wire loop of side 10 cm and resistance 1 ohm is moved with a constant velocity V0 in a uniform magnetic field of induction B, which is given as 2 Weber meter square as shown in the figure. The magnetic field lines are perpendicular to the plane of the loop directed into the paper. The loop is connected to a network of resistors, each of having 3 ohm. What would be the speed of the loop so as to have a steady current of 1 milliampere in the loop? Give the direction of the current in the loop. So we have a magnetic field B, and in this there is a loop PQSO, and that is connected with a bridge, and we have to find out the speed with which the loop is moving. Okay. And it is given move out with a constant velocity of V0. So it is moving outward with a constant velocity of V0. So we have to find out what will be this V0. So first of all, we are interested in this bridge, and this bridge is a Wheatstone balanced bridge, so we can find out its equivalent resistance. We say the resistance network is a balanced Wheatstone bridge. Wheatstone bridge. Therefore, the equivalent resistance of the bridge network will be coming as 3 ohm. Okay, because we can neglect this middle one is of no use. So this 3 and 3 will be in series, this 3 and 3 will be series, ultimately will leading that we have a 3 ohm resistance of this network. And in this case, it is also given that the square metal loop is having a resistance of 1 ohm. So therefore, the total resistance of the network, which is consisting of resistance network as well as loop, you can say total resistance let us call this R total will be equal to loop resistance and plus R equivalent. We get this as RT will be equal to 1 plus 3, which gives us that total resistance will be equal to 4 ohm. Now we can find out the induced EMF. Because value of current is given to us, we can use Ohm's law to find out the induced EMF. Induced EMF will be equal to I multiplied by the total resistance. I is given as 1 milliampere, so this is 10 raised to the power minus 3, and here we have 4. So our induced EMF will be equal to 4 into 10 raised to the power minus 3 volts. Now we can find out the speed, because induced EMF is related to speed as BL multiplied by V. So we know that induced EMF is equal to BL times V. So from here we can write our velocity is equal to induced EMF divided by magnetic field and length. So we get our velocity, induced EMF is 4 into 10 to the power minus 3, and magnetic field is given as 2 Weber per meter square, and this is 0.1 meter, and this gives us the velocity will be equal to 2 into 10 to the power minus 2 meter per seconds. And this was asked in the question, that what will be the velocity of the speed of the loop. So I have to steady current of 1 milliampere. And now we come to our last question, and this question was asked in the year 2011, and it says that we have a long circular tube of length 10 meter and radius 0.3 meter carries a current I along its curved surface as shown in figure. A wire loop of resistance 0.005 ohm and radius of 0.1 meter is placed inside the tube with its axis coinciding with the axis of the tube. The current varies as I is equal to I naught cos 300t, where I naught is a constant. If the magnetic moment of the loop is n mu naught I naught sine 300t, then the value of n is. So we are given this figure, and it is a long circle tube of length 10. So we are given this length as 10 meter, and its radius is given as 0.3, and it says that carries a current I along its curved surface, and our loop resistance this is placed inside this tube. Okay. And we have to find out the, basically we are going to find out the magnetic moment of this loop. From there, making a comparison, we are going to find the value of n. So let us first of all find out the magnetic field, because the circular ring, which is consisting of a wire loop, is going to behave like a solenoid. So we can say that magnetic field generated in the solenoid because the circular ring behaves like a solenoid. Circular ring behaves like a solenoid. Therefore, we can write that our B is equal to mu naught n times I. And here mu naught is the permeability of the free space and n is our number of turns per unit length. Number of turns per unit length, which can be written as n prime divided by L. Therefore, we can remodify that our magnetic B will be equal to mu naught, and here comes as n prime multiplied by I divided by L. And in this case, n prime, that is the total number of turns, is equal to 1, as there is only single circular turn. As only a single circular turn. Therefore, we get magnetically B is equal to mu naught I divided by L. Now we can find out the flux. Flux is our dependent upon the magnetic field as well as area. So you can say that the flux passing through the circular coil, if we give it written as phi, will be equal to B times A. A is the area of the circular loop. So A is our area of circular loop, which comes as pi r square, and we also know our magnetic field, so we can write that our flux will be equal to mu naught I L multiplied by pi r square. Now the induced EMF because of this flux. Induced EMF will be equal to minus d phi by dt. We substitute our, you can say, equation for phi. We get E is equal to minus d upon dt of, this is our mu naught I upon L and pi r square. And this can be further simplified as minus mu naught pi r square upon L, and this is our di upon dt. Now we are interested in magnetic moment, so we can write magnetic moment of the coil, if it is represented as small m, then this is equal to the current multiplied by the area. And we substitute the value. Yeah. This gives us that m is equal to minus mu naught pi r square divided by L r di upon dt and times pi r square. And in case I forgot to mention that the value of current I will be equal to induced EMF divided by R. Okay. So induced EMF we substitute here. So from here we get this magnetic field. And we can just make minor adjustment here in this equation. We get our magnetic moment M is equal to minus mu naught pi square R4 divided by R di upon dt. And we are given that the current I is equal to I naught cos of 300 t. So we substitute the value, we get our magnetic moment M is equal to minus mu naught pi square R4 LR d of dt, and this comes as I naught cos of 300 t. Now it is simple derivative. You can say this will be equal to, comes as 300 mu naught pi square R4 divided by LR, and we have here I naught, and this comes as sine of 300t. Now we are also given the equation for magnetic moment. So we can say given equation for magnetic moment, and that equation is given as n mu naught I naught sine of 300t. So we can equate them 1:1. We can say that we get this as magnetic moment is our n mu naught I naught sine of 300t is equal to 300 pi square R4 LR mu naught I naught sine 300t. So if you make a comparison, we can say that the value of n will be equal to 300 pi square R4 divided by L multiplied by R. And if we substitute the values, we get this will be equal to 300 multiplied by 2 by 7 whole square, radius is given to as 0.1 whole raised to power 4, and this is our 10 multiplied by 0.005, and this will be coming as 5.9 to 6, which can be approximately equal to 6. Therefore, value of n will be equal to 6. So this was the 3 questions asked in the year 1985, 1983 and 2011. These complete all the 3 questions. Thank you.